When asked which planet is the greatest, the answer is almost always the same. Earth. Earth is the best planet. And that's absolutely true. It's the only place in a galaxy of 400 billion suns where meaning, life, and consciousness are known to exist. That alone makes it extraordinary. But let's zoom out across the solar system. There's been enormous buzz around going to Mars, and honestly, it might actually happen. Mars is the only other planet in our solar system that humans could realistically visit. Mercury is scorching hot. Venus is even worse, crushing pressure 90 times that of Earth, sulfuric acid rain, and surface temperatures hot enough to melt lead. And everything beyond. Gas giants. You simply cannot land on them. So Mars is it, the one and only candidate beyond Earth. Though further into the future, some moons of Jupiter and Saturn could become intriguing destinations, though that's a far more daunting challenge. Here's the stunning truth. We are standing at the edge of one of the most thrilling turning points in all of human history. We are on the verge of becoming a true spacefaring civilization, a multi-planetary species. And the revolution that's making this possible has been quietly unfolding over the last decade. Reusable rockets. SpaceX Blue Origin, they have cracked the code. Launching into Earth orbit is now cheaper than it has ever been before, and that changes everything. We are actively industrializing the space just a few hundred miles above our heads at a breathtaking pace. Satellite navigation, communications, weather forecasting, climate monitoring, these systems have shaped our daily lives for decades, whether we realize it or not. But now, with affordable access to orbit, what's coming next is absolutely mind-blowing. Multiple crewed space stations will orbit Earth simultaneously. Scientific research in space will explode, both academic and commercial. Space tourism will become real. And communications? Hundreds upon hundreds of satellites like Starlink are already up there, with competing mega constellations racing to deliver high-speed internet to every corner of the planet. This acceleration is only going to intensify. And that's before we even begin talking about mining asteroids, building cities on the moon, or establishing colonies on Mars. Just in Earth orbit alone, the opportunity is staggering. But here's the catch. When a new frontier opens up, it gets crowded fast. The real estate fills up. Conflicts emerge. And in space, that means satellites colliding, orbits becoming dangerously congested, and the urgent need for rules to manage it all. What happens when two satellites drift dangerously close to each other? How do you even manage something like that? Do you assign specific orbits? Or do you build a framework, something like air traffic control, where everyone agrees on an avoidance system, so that when two objects get too close, they automatically steer clear of each other? That framework simply does not exist yet. Across countless international meetings and conferences, nations and global bodies are scrambling to figure out how to govern space. And it is a massive challenge, because it always is when different countries and competing commercial interests try to hammer out agreements on how to manage a new frontier. But ultimately, it is breathtakingly exciting because, as the legendary Carl Sagan once said, we are taking our very first steps out into the cosmic ocean. And the water, he said, looks absolutely inviting. So what kind of jaw-dropping opportunities are about to open up? We already know from experience aboard the International Space Station that microgravity unlocks extraordinary possibilities, developing revolutionary new drugs, manufacturing semiconductors in ways impossible on Earth, growing perfect crystals in zero gravity. The evidence is overwhelming that on-orbit manufacturing could change everything, especially in material science and the biosciences. And beyond that, when we push further out and build the infrastructure needed to venture deeper into space, the opportunities become almost unimaginable. Take asteroid mining. Some of the greatest conflicts in human history have been driven by competition over limited resources, leading to war, environmental destruction, and civilizational stress. But out there in space, resources are not limited. There are staggering amounts of raw materials waiting in near-Earth asteroids alone, accessible within decades. That fundamentally transforms how we think about growing our civilization. And crucially, it means doing so without further destroying the planet we call home. That is why the future of space exploration is not just exciting, it is genuinely hopeful. Because just 20 years ago, nobody could have imagined how many rockets would be lighting up the sky today. Returning to Earth and launching again, it's the kind of future that feels closer than ever before in the 21st century. Now, you could fly a rocket through the upper layers of Jupiter's atmosphere, where the density is still manageable. But venture deeper toward the core, and the pressure and temperatures become absolutely extreme. Scientists believe there are exotic materials down there unlike anything we've ever encountered. In fact, we don't fully know what sits at the center of Jupiter, which is exactly why a spacecraft called Juno is orbiting the giant planet right now, trying to unlock that mystery. The leading theory involves something called metallic liquid hydrogen, bizarre alien material that defies our everyday understanding. Send a rocket through that environment, and it wouldn't last long. It would be crushed, melted, and obliterated, possibly smashing into something incredibly solid at the very core. These are such profound questions that NASA actually built a spacecraft specifically to investigate them, and it's out there right now as we speak. Here's the stunning truth about Mars. No new technological breakthroughs are needed. We already have everything required to visit and eventually colonize the red planet. Mars is remarkably the only planet beyond Earth that humanity will realistically ever colonize. Perhaps some moons of the outer planets could follow, but Mars stands alone as our true second home. And here's why Mars is surprisingly achievable. It holds water in abundance, locked beneath its surface and frozen in its polar ice caps. It contains all the minerals needed to build a thriving civilization. We already know how to extract that water, split it into oxygen for breathing and hydrogen for rocket fuel, and generate the electricity to power everything. There's iron in abundance, essentially all the raw materials a civilization could need. We know how to do this. The rockets exist. The knowledge exists. The only question is when we decide to go. Anyone alive today could realistically walk on the surface of Mars within the next 20 years. Permanent bases could be established within that same window, built first by robots, with humans arriving afterward to move in and begin life on another world. It's not science fiction. It's an engineering timeline. Terraforming, actually transforming Mars's atmosphere into something breathable, is a longer-term ambition. But in principle, we know it's possible. Eventually, plants could grow openly on the Martian surface once conditions are warm enough. There's even a place on Mars called Hellas Basin, almost certainly a colossal ancient impact crater, so vast and so deep that its floor sits 9 kilometers below its rim. So enormous that if you placed Mount Everest inside it, you could look down on its summit from the edge. Because the summit would stretch beyond the horizon, it's that massive, consuming a significant chunk of the planet's surface. But here's the mind-blowing part. The crater is so incredibly deep that atmospheric pressure at its floor becomes extreme enough for liquid water to actually exist there. Right now, on Mars. So even with Mars's razor-thin atmosphere, certain low-altitude regions generate enough pressure for liquid water to appear, even momentarily. That changes everything. And the atmosphere of Mars doesn't need much to transform. Add some greenhouse effects, pump carbon dioxide into the air, and suddenly you can imagine plants taking root, producing oxygen, consuming that water, thriving. At some point in the not-so-distant future, Mars could have a full atmosphere again, because it had one before. Now, how many planets are actually out there? Just over 20 years ago, we had 0 confirmed planets beyond our solar system. 0. Today we know that virtually every single star in the sky hosts at least one planet. Data from the legendary Kepler Space Telescope suggests there could be 20 billion Earth-like planets in the Milky Way alone. We've already confirmed roughly 1,700 of them, and that number keeps climbing. So the real question becomes, could any of them harbor life? And here's where it gets truly extraordinary. Our telescopes can now analyze the chemical composition of a distant planet's atmosphere by studying starlight passing through it during a planetary transit. On Earth, oxygen is the ultimate biosignature. Almost all of it comes from photosynthesis. Spot a planet drenched in atmospheric oxygen, and you've got powerful evidence of life. But some scientists go even further. What if we detected industrial pollutants like CFCs in an alien atmosphere? Chemicals that nature simply doesn't produce on its own. That would be the signature not just of life, but of civilization. And closer to home, the search for life on Mars is intensely serious. We know liquid water once carved rivers across its surface. We strongly suspect liquid water still hides beneath it right now. Any microbes that evolved there, perhaps millions of years ago, could still be surviving in those hidden depths. Billions of years ago, life could have survived deep beneath the surface. So we may actually find life on Mars. And honestly, that could be one of the greatest discoveries in human history. Now, that's not a purely scientific statement, it's more of a feeling. But the reason we build massive spacecraft and send them to Mars is because we desperately want to know. We simply don't know yet. And if we already knew the answer, we wouldn't bother building the spacecraft in the first place. But right now, the excitement is real. When it comes to the question of life beyond Earth, the honest answer is we've found nothing. Not a single living thing beyond our planet. But to be fair, we haven't looked very far or very hard until now. Because right now, we are searching Mars intensely. And here's why that matters. Mars once had liquid water. It was geologically active. Every single condition we believe triggered the origin of life on Earth was also present on Mars around the same time, roughly 3.5 to 4 billion years ago. So finding evidence that microbes once existed on Mars, possibly underground, or even on the moons of Jupiter or Saturn where liquid water exists today, would not be shocking at all. But here's the critical part. Nobody expects anything more complex than a microbe. Look at the history of life on Earth. Microbes appeared around 3.8 billion years ago, almost immediately after Earth formed in geological terms. But complex life doesn't show up in the fossil record until about 600 million years ago. For most of this planet's existence, life was just slime. Single-celled organisms doing their thing, photosynthesis, basic chemistry, but nothing more complex than a single cell. Only in the last 500 million years did life explode into the dazzling complexity we see today. And modern humans, Homo sapiens, have only existed for less than 1 million years. Civilization itself, just a few tens of thousands of years old. So it took nearly 4 billion years to go from a single cell to a civilization. That's a third of the entire age of the universe. And that's exactly why many biologists now believe that while microbes might be everywhere, civilizations could be extraordinarily rare. In fact, when asked how many civilizations might exist in a typical galaxy like the Milky Way, the brilliant physicist Sean Carroll gave a stunning answer: none. Now, there are two ways to think about this. Let's start with the simple one and look at a planet like Mars. Mars is smaller than Earth. And what does that actually mean? It means Mars has a larger surface area relative to its volume. This is a fundamental law of physics. As an object grows in size, its surface area to volume ratio shrinks. Small things have lots of surface relative to their interior. Large things have relatively little. You actually see this in nature all the time. Tiny animals like mice and bats have to work enormously hard to maintain their body temperature, compared to massive animals like elephants, for exactly this reason. Apply that same principle to a planet. When planets form, enormous amounts of rock collide and merge together, generating intense heat deep at the core. Heat is also generated deep within planets through radioactive decay. A planet holds a certain amount of heat in its core, and that heat slowly radiates out into space. The smaller the planet, the faster it loses that heat through its surface, because the surface area is large relative to its volume, which is roughly proportional to the total heat stored. So a planet like Mars, being smaller, would eventually see its core solidify. Once that liquid molten iron core freezes, it can no longer spin and churn, and the magnetic field simply vanishes. That, in broad strokes, is exactly what happened to Mars. Jupiter is a far more fascinating case, because it actually generates its own heat. This comes from its ongoing gravitational collapse, the crushing pressures in its interior, and the condensation of liquid matter deep within. It's not a star, it's nowhere near massive enough to trigger nuclear fusion, but its sheer immense mass gives it a remarkable ability to produce heat from within its core. So the pattern seems clear. Jupiter is enormous and hot, Earth is large and active, Mars is small and cold, its magnetic field long gone. But then something extraordinary happened. Spacecraft flew past Pluto, a tiny frozen world on the very edge of the solar system, and discovered that it is geologically active, or has been in the very recent past. That means there is a heat source buried inside. How? Why? Such a tiny object should have lost all its heat billions of years ago. The honest answer is that we simply don't know. One leading speculation is radioactivity, that Pluto's core contains an unusually high concentration of radioactive elements for reasons we don't yet fully understand. And right now, the New Horizons probe is heading toward another distant minor planet to find out whether it tells the same story or a completely different one. This is one of the most powerful lessons science can offer. Just when you think you've found a universal rule in planetary science, the next world you visit breaks it completely. This debate is very much alive in space science today. Robotic probes like the Curiosity rover exploring Mars cost a fraction of what a crewed mission would. Many scientists argue the money is better spent on machines. And in terms of raw cost efficiency, that's a reasonable position. But human exploration is about something deeper. It's about learning to live and work beyond Earth, and that argument is genuinely compelling. Near-Earth orbit is already a multi-billion-dollar industrial zone. Communication satellites, weather satellites, GPS systems, humanity is already up there. Expanding further, learning to truly inhabit space, feels like a natural and inevitable extension of civilization itself. The resources available just beyond our atmosphere are almost incomprehensibly vast, and that changes everything about how we should think about our future. Believe it or not, in the asteroid belt alone, there's enough metal to construct a skyscraper over 800 stories tall and wrap it around the entire Earth. Now, nobody's actually proposing that, but the point is staggering. All that energy from the sun, all those resources, they're already out there waiting. You could almost imagine a future where Earth becomes a protected residential zone and all the heavy industry gets moved off planet entirely. It sounds like pure science fiction, except that reusable rockets are already a reality, and suddenly the economics actually make sense. Expansion is not just possible, it's inevitable. And the direction is outward, because there simply isn't much room left on this planet to grow. The frontier that once drove human civilization forward has vanished from Earth. But Mars? Mars could be that frontier again, with all the raw energy, the challenge, and the transformation that comes with pushing into the unknown. And here's the thing about Mars. When serious people talk about expanding human civilization beyond Earth, Mars isn't just the best option. It's the only option. You can't survive on Jupiter or Saturn. Mercury and Venus are death traps. Mars is it. And remarkably, almost everything needed is already there. Now, if the goal is purely scientific discovery, robots do the job perfectly well. But if the goal is civilizational expansion, humans have to go. Mars has a fascinating history. We now know quite a lot about it. There was almost certainly liquid water, possibly entire oceans and river systems. And that water hasn't disappeared, it's locked in ice, and there may even be pockets of liquid water hidden beneath the surface right now. Add in the rich mineral resources already confirmed, and Mars becomes genuinely viable. Compared to everywhere else beyond Earth, Mars is almost welcoming. Venus would kill you instantly. Over 400 degrees of heat and atmospheric pressure, 90 times greater than Earth's. Mars, by contrast, has gravity, roughly a third of Earth's, and while the radiation environment is elevated due to the absence of a magnetic field, it's manageable. Underground habitats, lava tubes, natural caves, these could offer real protection. And here's one of the most mind-blowing facts about Mars. There's a crater called Hellas, a colossal ancient impact basin so deep that you could drop Mount Everest inside it, and the summit wouldn't even reach the crater's rim. We're talking 6 or 7 miles straight down. At the bottom of that basin, the atmospheric pressure climbs high enough that liquid water could actually exist on the surface. On Mars. That's not science fiction. That's real planetary science, and it changes everything. Occasionally on the floor of that crater.